Hello everyone. This lecture will be about the classical consensus. So what is a consensus? A consensus is a mechanism by which we want to find an agreement, right? If we are like three people and we might not, we might search a decision on a particular problem, right? Should we do A or should we do B? Right? Then we want to find an agreement among those three people. And how can we do so? How can we exchange information? In what way? When do we talk to each other? How often do we have to talk to each other? What if one person is not reachable? Do we still decide or not? So a lot of questions that kind of come up when you think about consensus and how to reach consensus. So the first thing is the different timing models that we want to look at. So these can be asynchronous, synchronous, or eventually synchronous. So the asynchronous one is the one that's the closest to reality, right? It's the one where when you send the message, it will be eventually delivered. At least this is true for standard internet IP protocols, right? If you send a message over TCP, it will be resent if it's not acknowledged by the receiver. So it will eventually be received. The problem is you don't know by which time it is received, right? So the time here is a question mark. It's a question mark, which means you don't really know by what time, what deadline it gets received. So in order to make some analyzers simpler, some design analyzers simpler, researchers have proposed the synchronous model. So this means that there is a guarantee on the time of delivery, right? It guarantees a certain time. So a message is sent at time t, and you know that it will be delivered at time plus x. So that's a delta that you're aware of, that it's kind of your upper bound on the delay of reception at a particular peer. And eventually synchronous is kind of a mix between those two. So you have some known upper bound on the delivery time, but this upper bound is variable, so it might change over time. So what about the possible fault models? What if some peers now suddenly break? So I had this image at the very beginning that I drew, like three people talking to each other. Basically, a faulty process is a person that is not responding, for instance, or that's responding in a malicious way. And what you can typically see is that people or researchers write like you have an F out of N processes that fail, and this basically means like F out of these N peoples, they fail speaking or they fail to communicate to reach a consensus. And what you can often see is this F smaller n over 2 or F is smaller n over 3. Now obviously you can have different modes of failure, right? You can have honest nodes that remain available and they do not anything Byzantine, so anything malicious, right? And they can suddenly fail to be available, right? So a node might crash, your internet connectivity might drop because it's not very stable. But you can also have a malicious entity that might inject packets that are maybe not protocol conform, or that might break other nodes. So this is a so-called Byzantine failure. And then we have different broadcast models. So there's notably the consistent broadcast and the reliable broadcast model. So in a consistent broadcast model, corrupt sender implies that not every party might terminate or deliver requests. Right? That's the consistent broadcast model. In the reliable broadcast model, so if we have a sender and he emits a value v, then we have termination if the sender is honest and the correct party outputs the same value v, right? So what the sender emits is output by a correct party. We have the property reliability. If every correct party also outputs V. And we do have consistency. This means if we have two distinct parties and they each output V1 and V2, and those two are equal. So these two parties are consistent. So there are a bunch of classical consensus algorithms that were proposed over the last 30 or more years. So some of the most famous, more famous ones are PBFT, Paxos, Raft, and others. And they're basically some of the common features of consensus protocols is that you have some sort of a leader election. So some node is at a given point in time a leader, and eventually this is something that's shared among all the nodes. So everybody should eventually become a leader. Now, obviously, this depends a bit on your protocol. There might be some where you have so-called leader nodes or master nodes, and then you have other nodes and that are maybe more listening, and these listening nodes, they might not become a leader. So this really depends a bit on your protocol that you're looking at. So safety is quite an important element of these consensus protocols. So you want that the output is guaranteed to be consistent, right? The previous slide we defined consistency, even under an unstable network and malicious leader. So even if this leader that gets elected here is malicious, we want that the output of the I or N parties is consistent. So it means same output. If the sender sends some value. And although in reality messages are passed around in an asynchronous manner, eventually we want to reach a synchronous network. Liveness is another property, which means if there's no progress, we have to elect a new leader, right? So if you have here 3 nodes and one of them is a leader, so we're passing around leadership, and at some point in time this one here doesn't respond anymore, then the leader election has to automatically pass to the next one so that we can continue the consensus protocol, that we can go on, so that a faulty leader that just, for example, crashed doesn't stop liveness. Without liveness, we don't have progress. Without progress, we cannot reach consensus. So if the network is stable and we have an honest leader, then we must have liveness, right? Because if we don't have liveness, then the consensus cannot be reached. So there's this known impossibility result. This is from Fisher, Lynch, and Patterson, 85. And it's also referred to as the FLP result. And it states, in a fully asynchronous system, there is no deterministic consensus solution that tolerates one or more failures. So basically, there's no algorithm that can always reach consensus in a bounded time. And one of the important implications of this FLP result is that timing assumptions are really required for every protocol, right? So you must have some kind of a deadline on, for example, when to receive a message. So it has to be, you need to have some delta, right? So it should be eventually synchronous. Another implication is that randomness is really crucial. You don't want a leader to know that he will be elected next, right? I mean, ideally, you really have some strong randomness that makes it harder for an adversary to be elected as a leader, for instance. Because this could delay the consensus protocol, and then hence it delays your progress and your liveness. So given any protocol that you're given, right? I mean, there are many consensus protocols out there, many proposals. Given any protocol you're reading up, you're hearing from friends about, I can recommend you to think about the following questions. So, is the FLP impossibility result respected? Right? If it's not, then it might be shady. You might want to look into it more, right? Why is the FLP result not respected? Second, what's the message complexity or the number of rounds that are required for peers to reach consensus, right? How does it scale with the number of nodes, right? How many nodes are allowed to fail? Where does the randomness come from? Can you somehow attack the randomness? Is there some way for you to be elected as a leader? So can an adversary manipulate the randomness and become a leader over and over again? Okay, so these are kind of critical questions you should ask yourself. So Raft, I can recommend you going to this URL, raft.github.io. It's just an example, a visual example on how you can Raft works, and you can try it out yourself on your browser if you're curious. So now you might ask, how does this all relate to Bitcoin? I mean, what's the relationship to proof of work? So in proof of work or in permissionless systems, right? There's no, at least in permissionless systems that are proof of work based, there's no need for final consensus output. You have, for example, the longest chain rule in Bitcoin or Ethereum in the proof of work versions, and you don't get 100% finality, right? You have a likelihood that the chain that you're currently on, or that has been mined on, this chain will likely not be overwritten by somebody else who is attempting to fork the chain, right? So you have a probability that tells you it's unlikely to be overwritten. But there's no need for final consensus output. At least you might say there might be a need for it. Maybe, it would be nice to have one. But it's not absolutely required for the system to function. In Bitcoin, blocks and transaction rewards are kind of the incentives to participate in the system. And I think the crucial differentiation to PBFT, Paxos, and the other protocols is that in permissionless systems, the participating nodes are not needed to be known upfront. Right? So you don't know necessarily who or how many peers are participating, and this is probably the fundamental difference. So you have permissionless versus permissioned systems. Right? That's probably the biggest difference.